technischer. Also ich als Herald, um die anzukündigen, kenne die eigentlich auch nicht, weil die waren billig. Ich weiß auch nicht, was die drauf haben. Die kommen hier aus der Nähe, aus Bonn. Also die Fahrtkostenerstattung, die haben wollten, war halt 0. Und da haben wir die einfach genommen. Und ja, die sehen auch nicht seriös aus. Also ich weiß auch nicht, was sie uns erzählen wollen. So, nee, aber ich glaube, wer hier sitzt, der weiß, glaube ich, dass es technischer wird. Der weiß auch, was hinter Malware sich verbirgt. Und der weiß auch, glaube ich, mit den Namen Felix Leder und Tilman Werner auch von der Uni Bonn etwas anzufangen. Wenn man mal so ein bisschen professionell mit Configure zu tun gehabt hat, beziehungsweise Anti-Malware, dann weiß man die Forschungsarbeit der beiden zu schätzen. Und deswegen freuen wir uns besonders, dass wir hier so Experten an Malware vor Ort haben und die bereit sind, aus dem Nähkästchen zu plaudern und einfach von ihrer Arbeit zu erzählen.
Okay, thank you for the introduction. So originally we planned to give this talk in English. Is there anybody here who doesn't understand German? Okay, so we stick to English. Very good. Okay, so the story today is about Malware Joe, right? And Malware Joe wants to build up his own botnet or malware. And we'll have a look on what Malware Joe needs. And actually, that's him, right? That's Malware Joe. And the first question, if you want to build your own botnet, is do you use commercial off-the-shelf stuff, or do you create your own handmade malware? So actually, there's the Zeus builder. Nice program. You just enter some configuration details and click on Build Executable, and you get a nice executable that can spread over the internet and so on. And this is really good stuff, right? You can own lots of banks and people, and well, when you got good quality software, you should pay for it, right? You pay for music, you pay for television, so also pay for good quality malware generators. And the Zeus builder includes like a licensing management, and the problem is, well, it's hooked to your PC. So if you get a new PC or a new machine, you got to get a new license. So in the end, you got to pay 5,000 euros, about, roughly, depends on the reseller, and then you get a nice Zeus builder. And actually, when you don't have a license, you see this message, and in the end, we are meant in the last line, it means you stupid crackers.
Okay. By the way, as they are going commercial now, it's going to be interesting to see when they will eventually be using our security services like building certs, you know, issuing patches, stuff like that. So that's going to be fun.
The problem is those people using builders to create malware, they are usually not the smartest, or they are not the technical persons. So the problem is very often they get infected, but luckily the Zeus builder also has a disinfection tool for self-made binaries. So Malware Joe would be safe to use one of those things, but the signatures from antivirus, they are very good. They detect Zeus, and that's a problem. So what Malware Joe does, he decides to, well, create his own malware, which is customized and has some very good protection mechanisms that you don't, for example, find in Zeus.
Right.
Okay, first of all, Malware Joe, we're talking about virtual machine detection. He wants to make sure that whenever he gets a machine that is controlled by an analyst, virus analyst, which is very likely a virtual machine to step back to the original uninfected state, that the analyst has a very hard time to figure out what this malware does and how to create signatures. So first of all, he has to make sure that some virtual machines he's infecting, you got to make sure they are really analyst virtual machines and not just any virtual machines, because nowadays there are lots of servers that are using virtual machines and he doesn't want to infect those. So, but being on an analyst machine, normally analysts do sandboxing. That means they are lazy, they just execute the malware in a virtual machine that has automatic analysis tools, and in the end they get a trace like this. This is a screenshot from the Norman sandbox. It tells them which registry keys get accessed, created, modified, which files are open, network data, all those things. And Malware Joe wants to make sure that his creation doesn't tell anything to the analyst.
Yeah, well, maybe a little word of warning, because we are not really fans of this dynamic analysis, because we believe in static analysis because it tells you much more. So the word of warning is that the next couple of slides will be bashing on this dynamic analysis approach. So, well, if you're a sandbox developer or if you like dynamic analysis, sorry, but it's necessary.
You fail. No, okay, here's the big problem. Symantec, for example, they collected 2 million samples, new malware samples last year. And if you do your math and calculate how many seconds a year has and so on, you see that actually you only get 10.9 seconds for every sample to analyze. Problem is, in 10.9 seconds, that's shorter than my Acrobat reader requires for starting up. So even with malware, you don't see a lot. So that's why normally sandboxes run stuff for 2 to 10 minutes to actually see something. But the problem is you need more and more sandboxes, the more malware you get. And there's a simple sandbox evasion. If you think about 2 to 10 minutes until, well, for the whole process to monitor a malware. And this is from Storm, the newest version from, I think it started April, beginning of April. So what Storm does at the very beginning, who can tell me what this means?
By the way, quick show of hands, who knows what the stormworm is? Are you familiar with that thing, stormworm? All right, so that's a piece of malware that used to spread, I think, starting in 2006 or 2005 already, so it's rather old. And it was responsible for most of the spam emails back then. If you have ever received such an e-card exe spam mail, or that was the spreading spam, and then also the advertisements for this Viagra shop in Canada, that has been Storm. Okay?
And the authors of Storm, right, which is Malware Joe, they know how to evade sandboxes, because before they are doing anything, they wait 10 minutes. This means every sandbox has already timed out and they don't get any reports at all from this malware. The problem is there are some very smart sandbox developers as well. And they say, okay, whenever I see a sleep with a long timeout, I just shorten the timeout and make it very much shorter so that the stuff starts running earlier. So what would be the defense against that? Well, you create a long loop that actually does some calculation. That takes 10 minutes. And this is actually from Zeus, stuff we had on the first slides. And Zeus has like a random number it puts into every binary that it creates. And furthermore, it calls an API function from Windows. And calling an API function is tricky because some people think, okay, I see the original source code once a malware starts calling Windows API functions. Before, it's all like decryption and sandbox evasion and stuff. But once they are like real calls, except of sleep maybe, then normally the stuff is unpacked, unencrypted, and you can read the source code. And with this, they even evade this. They can make sure that sandboxes don't see anything and packers or automatic unpackers break early.
Okay. By the way, whenever you have any questions, you don't have to wait until we finish the presentation. Just feel free to ask them right away. I don't know, yell at us or something, so we see you actually got a question. Okay?
So sandboxing fails. We have already seen this. So how about manual analysis? Go there, take a debugger, step through the assembly, and try to extract the information that you actually need. Okay, are there any anti-debugger mechanisms out there? Well, the easiest way is actually already attach a debugger, because when the second debugger comes, well, it can't attach anymore. There's only one debugger allowed per process in Windows. So what the bad guys do, they spawn another process, which is a debugger, a pseudo debugger, and attach to the original malware. And then nobody can attach another debugger to it. Okay, there are some tools, also like similar to sandboxing tools, who monitor everything that's happening in the malware, every instruction that gets executed, and every memory access that gets executed. Why is that? For example, you want to make sure that you see where the decryption or the packer ends that you have in malware. There's one problem. This whole thing, monitoring every instruction and monitoring every memory access, that costs a lot of time. And even if you do this in a virtual machine environment, the real-time clock still continues. So in the end, all you have to do is take a start timestamp, do something and of what you know, how long it takes, take another timestamp, compare the timestamps, and if it took longer than something that is normal, you know that you're monitored and you can do something else. For example, take a completely different branch, serve to porn sites and so on, and that's how some research is sometimes done. Whenever you see approaches that try actually to really monitor all of the, well, memory accesses, be skeptical about it, because sometimes they are seeing different stuff. This is another example how you can do it using the real-time clock. This is from WhaleDeck, another botnet that has been quite big last year.
WhaleDeck? Who knows WhaleDeck?
Who knows WhaleDeck? Okay.
Well, you guys aren't really following the malware news then.
Don't worry, we'll show you the main aspects of those. So actually you can see here WhaleDeck is using this. They are doing some stuff for about a minute, 10 minutes, 60,000 seconds. And after 10 minutes, it does something else. So when you look at those memory tracking approaches, they normally are 2,000 times to 4,000 times slower than the original malware. And you can make sure that in those 10 minutes, not the same stuff happens as they would normally. Like there's less stuff that can happen. So this.
Oh, sorry. We from time to time we make little mistakes during our presentation in order to check whether you're still with us. And of course, this is milliseconds, so not 10 minutes. But as nobody of you mentioned that, I have to mention that. Okay. Sorry.
That's right. I should have had a look at the slides before, maybe. Okay, so here we are at the defensive techniques, right? And was a quick overview. Quite some sophisticated stuff, but the problem about Malware Joe is, even though he's pretty good at what he's doing, right, he's just human. And who of you has never made a mistake? Oh, wow, okay. Well, so all humans, they are not unfailable, so they fail, and so do malware developers and bot herders. This is from 19th of May, so just a few days ago. Actually, it's a Zeus drop zone. And on the server where they collect all the key logging data and all the bank accounts, pins, TANs, everything that you need, Facebook accounts, by the way, porn sites, whatever you want, everything gets dropped there. But they forgot that they haven't set a password for the root user, and they even have PHP admin on their website. Right?
By the way, before you go into the details of this Zeus thing, should I ask who of you know Zeus? All right, the same guys again. Okay, so Zeus is a piece of malware that hooks into the browser, okay? And whenever you enter something in forms, maybe even using an SSL encrypted session, then Zeus grabs this data and sends it to a drop zone, a central site somewhere on the internet. And there this stuff gets collected, like, you know, banking credentials, porn site credentials, stuff like that. And of course it's stuffed in a database there, and well, these guys here failed.
Yeah, so actually we had a nice overview about everything that was happening in this botnet, because for every day there's a special table created, and we could have a look in there if we find some nice porn credentials, because we are poor students and cannot afford it ourselves. So we were lucky in that case, and also some other interesting account data. And furthermore, there is a table that is name, pass, language, and some flags and so on, which is actually the credential for the management platform of Zeus, of this bot, okay? So the whole botnet can be controlled using this management interface, and here, that's the admin account and the password. Unfortunately for us, this is MD5, and we don't have any means to crack short MD5 passwords, right? Okay, so rainbow table, a few minutes, and done. So even if they set a root password, we will still be able to have a look at the bot reports, very kind of them. Because of using MD5 there. Okay, that was the first fail. Let's have a look at the last fail. But, well, everybody can fail, even the smart guys. and how smart they are, we want to show you first, and then we show you how fail they are.
Well, I guess it's my turn now. And I wonder why you always present the fancy slides with pictures and stuff, and I always have to present the, this assembly thing. Anyways, so is this actually working? No. Okay. All right. Maybe you know that whenever you analyze a piece of malware, what is very common is that the original code is somehow obfuscated, okay? Because it hardens analysis. And the most common way to do that is to encrypt it or to pack the code, and then you have to, before you can analyze it, you have to unpack it or decrypt it, okay? And this is also done by Whaledeck. This is the most recent version. As Felix said, the botnet is not live anymore, but this is the last version. And we had a look at the obfuscation, and I would like to briefly tell you how that works, because I think it's rather interesting. So when you throw the code in a debugger, what you see is, let me see, what you see is this part here. So this is what the assembly instructions you see when you attach a debugger to the process, or when you load it in the debugger, okay? And I mean, even if you don't know assembly very well, you can already see this is not really much code here, right? So this is a function that stops here, and this function is calling another small function consisting of like 8 lines of assembly code. So there's nothing really happening here. But we know that this is a, I don't know, piece of malware that connects to HTTP servers, stuff like that. So where's the code? Where's the interesting part here? Can I click with that? Mm-hmm. Oh, great. So what this does is, this function here does some less important stuff, and then it calls the second function. Okay, function calling the second function, not very interesting. And then you single step through the code line by line, and you try to understand what it does, and then you eventually end up at this instruction here, which copies the EAX register to some memory location, or I think it's a subtraction. Anyway, so it modifies some memory location, and it's not possible because that memory location is write protected, okay?
Has anybody here ever tried to program in C and wrote something to a null pointer? Come on, there must be more. So this is actually what happens here, but it's not a null pointer, it's some other memory location where you are not allowed to write to.
Okay, what happens? As usual, this throws an exception. Okay, on Windows you have this model of exceptions. An exception handler gets called that usually terminates the program or something. And well, okay, in this case, you trigger an exception by doing this. But Whaledeck does it intentionally. Okay, so it's part of the control flow to trigger this exception. And on Windows, you can actually register your own exception handler, another function, so to speak, which then gets called by triggering the exception. And the exception handler is actually the code starting with this instruction here. So this part here is the exception handler. All right. And let me see, what's on the next slide? Yeah, the exception.
Right. So maybe just a quick addition to that. So normally when an exception occurs and you're running a debugger, the debugger will stop the execution there and will stop the whole program from running. It will like interfere with the original exception handler. And so this is kind of a debugger detection that is often found in malware. But the stuff here is even a little more sophisticated.
Right. I mean, it makes good sense for a debugger to catch exceptions because it's debugging, right? You want to find your bugs, and normally if you see an exception, that's probably your messy code. But in this case, as I said, it's intentionally. I also have to tell you, there is this EAX register, some CPU register that gets initialized with a certain value, and this basically serves as a loop counter here. So whenever you, I think I should tell you, when you finished handling this exception with this code here, you end up at the same instruction again, and again you trigger the exception. Okay? So you end up handling exceptions all the time, basically. Okay? But in this very case here, you have the EAX register, which gets decremented for every exception you handle. And at some point in time, it reaches this value here. At some point in time, it's 1. And the funny thing is, if it's 1, then the exception handler is a different one. Suddenly, the exception handler is the code down here, and not the code up here anymore. So, well, that basically is for making analysis harder. If you imagine single-stepping through this code, I mean, single-stepping through 15,000, that's a hex value, so it's much more in decimal, exceptions, you really don't want to do that, and it's very hard to use breakpoints here.
Because normally you have to press F7 for every instruction.
Okay, so it's thousands times of pressing F7, so you don't want to do that. Okay, all of a sudden you end up at this part here, which is not interpreted as code yet, but all of a sudden it is. Question? All right. So all of a sudden you end up at this very code here, this exception handler, and what happens here is that you initialize some value, jump down here, and then we call the int to e assembly instruction. And this is triggering a software interrupt, okay? And in this case, it's the access check software interrupt, and that fails again. So again, we try to access check a memory location that's invalid, so we get an exception. And in this very case, what happens is that you get an error code in EAX, in the EAX register, which tells you access violation. And you also get the address of the failing instruction in the EDX register. So another register that then points to the instruction following the failing one. Okay? That means all of a sudden you have a pointer to your own code by triggering this exception here. Okay? Got the idea? And then you can use these two values to derive another value, which is then the offset where you want to continue execution. You get the idea? I mean, this is something you see in malware from time to time, but it's very rarely is as complex as in this scenario here. So you trigger some exceptions. Those exceptions provide you with pointers to your own code, and then you take these offsets to derive where you want to continue execution. So this is really, really hard to understand and to debug in a debugger. And furthermore, it fails in VirtualBox, which is a virtual machine. Lots of people use it for malware debugging. So if you're running VirtualBox, this fails. It also fails if you are using OllyDBG, a debugger, a very popular debugger, or Immunity debugger, which you see here. So if you have one of those two debuggers, this doesn't work. Why doesn't it work? Because the EDX register isn't loaded with the offset of the instruction following the failing one, but it's initialized with this value here, which is -1. So you can't derive the next step from that, okay? I mean, if you are not really into VirtualBox core development or these debugging stuff here, you basically don't know. So you have to find out why this doesn't work in VirtualBox or in when you have a debugger attached. Okay, the next step is now that you can derive that value, let's assume we can do it. We push that value on the stack, we return to the original code up here, and then this code again calls a return, which means it takes the topmost value from the stack and returns to this address. So this is like an indirect function call. Okay, for those of you who are not really into assembly language, all that stuff, I know it might be a bit hard to follow, but this is how it works here. And for us, it's important for you to get the idea. Okay, next step is that this is the return to the EAX then. And where do we return to? We return into a multi-stage decryption routine. Okay? So now we are at the stage where we actually decrypt the original code. And this is multi-staged, okay? And it's also position independent, so it tries to find its own position in memory and then it starts to decrypt itself. Okay, that's basically it. Bottom line is, this is really, really, really smart. You rarely see cool stuff like this in malware. So we can safely assume that Weldec itself is also very smart. Can we?
So actually this is as smart as if you were working at an antivirus company, you would definitely need a senior analyst to look at this and cannot take junior analysts. Maybe you even need the boss or the CTO to have a look at this because this is really, really advanced and sophisticated.
Okay, so we took a look at this part and said, okay, I mean, actually we already knew the inside, the original code, and we knew that it was failing again. So yeah, well, Felix, tell us.
Okay, here is like a brief overview of the Weldec botnet. The purple nodes you see are like infected nodes you could think of. And whenever an infected node wants to know what are the newest commands, it's asking another infected node, like this one. Then the request is forwarded to another node, to another, until it reaches the command and control server.
The red one for you guys over there.
Right. Over there, you see like the leftmost purple node is the actual node that wants to get commands, and then you have some intermediate nodes that forward those requests. So actually, this is pretty smart because in the end, you don't know which is the command control server because you are only communicating with the next peer level and not with the actual command control server. Nobody knows where it is located, what it does, who is working on it. Maybe it's in Russia, maybe it's in China, maybe it's in Germany. Nobody knows because you are only talking to other infected nodes. And sounds pretty smart. But the problem is it's not active anymore. And I think it was the 28th of February, or was it 22nd? I always forget the date. But there was one date when this whole botnet stopped working suddenly. And why, we're going to tell you soon. Actually, it's all because it's a big fail. Maybe we'll have another look at the structure. You see in the structure that it would be cool to be one of the nodes in the middle because then you can intercept commands and see who is getting which commands and so on, and maybe even manipulate them. The problem is, how do you get one of those intermediate nodes?
Yeah, maybe let me go to that mic. Maybe for you to understand why you want to have a multi-tier architecture. The way that authors understood that there are two different qualities of systems they can infect. There's the ones that are behind network address translation, like you, if you're running a Fritzbox at home and stuff like that, you are not directly reachable from the internet. You all know that, right? So these nodes cannot be part of the structure here because you cannot connect to them. But you can use them to send out spam, to perform DDoS attacks, because that's only our connections, okay? And then there are nodes that have a public IP address. That means you can connect to them from everywhere on the internet. And these are the valuable nodes. These are the ones you want to create your infrastructure from, okay? So they distinguish between relays, on the one hand, the high-value nodes, and the others that are behind network address translation, and they shall be doing all the work, like spamming, DDoSing, stuff like that, okay? That's the reason why they build up this architecture here.
Right, so when you're a relay, you can really see all the traffic that gets relayed, like a proxy server, like a web proxy. And if you're just one of the outside nodes, you're just a worker. You're just spamming, sending DDoS, collecting credentials, and so on. So for us, as researchers, we would like to be relay nodes and not spamming nodes. So there are two possibilities to actually become a relay. First of all, you just put some node in the internet, no firewall, no protection on there, get infected, wait for 45 minutes, like an hour, and then suddenly, well, you're one of the relays because the botnet sees that you're a very good node and can relay traffic, so you're one of them. Or you use the command line switch. We think they have put this in for debugging purposes, but actually it's pretty helpful. There are 3 different command line switches which you can see. There's -S, -R, and update. So by using -R, you become a relay right away. Actually, there's some more stuff involved in there, but actually, yeah, in the end, it's just the -R that you need.
-S is if you want to be a spammer, by the way.
Right. If you never want to be a relay, just say -S and you can spam forever. Which is pretty cool if you are into spam analysis, because you're getting all the spam templates, right? Okay. This is the command layer, like the protocol stack. There's XML, there's bzip, there's AES encryption, there's base64, and also web upload. Wow.
But Felix, maybe one step back. You all know how botnets work, right? You have some command and control entity somewhere, maybe a server or something more complex, and then you have all the infected machines. And the whole purpose of a botnet is that there is communication between the CNC server and the infected machine. So you need a protocol in order to provide commands to the bots or advise them to do this or that, okay? And I mean, if you want to run a serious a stable botnet, a cool botnet, you have to worry about the protocol. And this is the stack of the Weldec CNC protocol.
And they have all the modern technologies in there that you need. Even RSA, okay, RSA is not a modern technology anymore, but...
yeah, but base64, as we've learned yesterday.
Yeah, base64 is the ultimate achievement for preventing SQL injections, right? We learned that yesterday. So high-tech stuff in there. And you can also see RSA is in there. So we thought, okay, even if we can become a relay, we can't snoop on the traffic because they are using RSA and AES, which is pretty much unbreakable. I don't know if you have a machine in the basement that can break RSA. We don't, unfortunately, because we are poor university students.
Well, depends on the key size. But
So, yeah, actually, RSA, we found out that there's a possibility to play man in the middle. So we broke the RSA key, you could say, and we had a look at the session key that is used for communication, which is AES.
this is much like in SSH or SSL connections, right? You have a private-public key pair in order to establish the session, and then you agree on a static key for symmetric encryption, right? Because it's much faster. You always use these hybrid schemes, right?
So, right. Public key encryption is just for key negotiation, and then you use a symmetric encryption or decryption routine, which is much faster for actually exchanging traffic. So we had a look at the session key that they were using, the symmetric session key, and we noted down like 4 different keys that we found over a period of several months. I think they forgot to seed their random number generator. So, in the end, there were just a few keys that they always used, and we wrote a nice web surface like this, a web application, where people could just paste their RSA encrypted request they saw, and we could decrypt them and told them we can break RSA with our little machine here.
And to be very clear, there's absolutely no point in using RSA, a public key cryptography scheme, to agree on a static key. That's completely bullshit. They didn't understand what they were doing here.
But they used advanced technology.
They did. Actually, they used OpenSSL library for that,
Yeah.
which is supposed to be secure and, well,
Except of the random number generator. Okay, here are some, before we continue on Whaledeck, actually here are 2 names that you should definitely remember. One is Greg Sinclair, who did most of the reversing that we have shown you together with us. And he managed to, well, kind of hack into one of the major command and control servers. So he got a better overview about which nodes actually have which role to play and who's involved and where the major command and control servers are located. So, yeah, smart guy, broke into their command and control servers and got all the data that we needed to actually get a whole overview of the system. Then there's Ben Stock. He looked at the different commands and he monitored the whole botnet for a very long time and found out that actually it's possible to put your own relay peers into all of the intermediate nodes, which allowed in the end to redirect all nodes to one single machine that we control. And, well, the end of the story is?
by the way, I mean, what that means is that you can control the botnet yourself. Actually, Ben is here today. I don't know. I'm not sure if he wants to stand up and, well, he's in this room today.
So, yeah, he had to do some work while he was on skiing holiday. And the end of the story was that we had some cooperation with Microsoft law enforcement all over the world and so on. And there was one day, bang, we took over the whole botnet. Actually, we still control it, or some people of the group still control it. It's not us. And yeah, Microsoft gave out this nice blog, and well, Whaledeck's not operating anymore. So completely failed, and well, they paid the price.
Well, go ahead, Felix.
Okay. Poison Ivy is a remote administration tool for mass remote administration. So in the end, it's a, well, botnet creating toolkit. And you can get it for free, poisonivy.com or something, I think is the URL. You can play around with it. And there's one guy, I can't pronounce his name because it's really complicated, but it's written down there. And he managed to crash the control interface and he did not only manage to crash the control interface, but also to inject his own code into the management, into the major control interface, which means he can take over all Poison, Ivy, command and control servers at once. Sorry, we can't share the details about how this works, how the exploit works, but it's another point that, well, sometimes bad guys, they do mistakes that lead to buffer overflows, and you can use those to take over the botnet.
All right. We've been talking about Storm already.
There's a question. Yeah, no, actually, I think it was the F-Secure blog where it was public, but Heise wrote about it, yeah. Yeah. No, we are not involved in that. It's not us. It's just this guy, I can't pronounce his name, sorry, otherwise I would have said it.
All right. Yeah, we've been talking about Storm already. Storm was a peer-to-peer botnet, and they used this. I mean, if you want to create a new peer-to-peer botnet, you have a problem, because it's very hard for your second peer to find the first peer in your botnet, right? That's not so easy unless you know where the first peer is. So what you want is an existing infrastructure, and then you want to use this for your peer-to-peer botnet, which makes sense. So the gang behind Storm, or the guy behind Storm, said, oh, well, there is a rather large peer-to-peer botnet out there, which is already up and running, very stable, very popular, which is the eDonkey peer-to-peer network, the file-sharing platform, right?
Who of you has ever used eDonkey?
Only one person, of course. Most of the times it's zero, so, well. Yeah, we agree that BitTorrent is much easier. Anyway, so there is this peer-to-peer network, which is still, the eDonkey network, which is still available today and rather large. So why not use this peer-to-peer network to build up a botnet? I mean, you can use the protocol for something else, something other than sharing files, searching for content, stuff like that. And the Storm guy said, okay, we do that. But it's very hard, you know, to come up with an own implementation of the peer-to-peer protocol, which is the Cardemia and what's the name of the other part again? Overnet, yeah. Those two protocols. So, I mean, you have to really understand this protocol, and then you have to come up with a flawless implementation, which is hard. But fortunately, there is an open source library available for that, which is the CardC library, Cardemia C library. So they used that. And then at some point in time said, okay, now our peer-to-peer botnet is big enough. We don't need the eDonkey stuff anymore, because, I mean, we are relying on third parties, so to speak, infrastructure, which might be a problem in the future. So let's separate. Let's separate. And how can you separate? You can modify the protocol you're speaking, right? So then you have your own separate botnet, and you're not relying on eDonkey anymore. And what they did was, well, I think not really the best, but a fairly good idea. They said, okay, we encrypt all the eDonkey messages with a XOR key. So we XOR those messages with a certain key, and then whenever we receive something, we XOR that again, so we decrypt it, and the rest can remain the same, all right? But they were using this CardC library, and they don't want to mess with, you know, other people's code. They don't even want to understand this code. So what they did was, I think it's on the next slide, right? Yes, they said, okay, we take stuff, we XOR it, then we stick it into the CardC send to thing, so it's sent out on the internet. And now we don't know what CardC is doing afterwards with the message. Maybe it needs it to, I don't know, update a routing table or something else. So they did not really understand what they were actually doing, but to be on the safe side, they unencrypted the stuff again after sending it out on the internet. And that's not necessary, because nothing happens with that data anymore afterwards. But they didn't really, they didn't even take the time to understand the CardC library. They just used it as a black box, and to be on the safe side, they had to decrypt stuff after they send it out. Okay? I mean, you could argue that from an engineer's perspective, that makes sense, because you don't want to spend time on understanding other people's building blocks. You just want to use it. So, well, but still, we rather like to see that as fail.
Yeah, so the original version of Storm had a little typo in there. Maybe you can spot it, right? When they were asking for, well, HTTP updates or something, they said Windows. And you see the whole user agent of the first version from 2008 in the upper box. And they saw that there are lots of snort signatures and all kinds of things that can actually detect this user agent and make use of it to detect Storm. So they said, okay, for the new version in 2010, we're going to change that so that we don't get detected that easy anymore. And what they did is they removed the last 3 characters. But unfortunately, they didn't notice that their mistake was the little typo of Windows. So unfortunately, the same signatures still work.
All right, so I think time is over already, but we won't let you out because now that's the most funny part, we think, the configure part. Again, the question, who has never heard about configure? Who knows what configure is? Great. Yeah, because it was one
Who
of
was
the...
not infected is
Yeah,
the better question.
The e-donkey guy.
Yeah, probably you need some antivirus that detects your configure infection at home.
Well, you can, if you want to be infected with configure on Linux, you can try wine.
If you get into problems, we can help you.
All right, so you all know what configure is, and you all know that basically every system that could be infected was infected. And amongst the infected systems were some rather interesting ones. For instance, that database server from the French Air Force. This one here, yeah? Well, that database server was maintaining the flight plans for those jets here, and it stopped functioning. So as a result, those jets couldn't take off anymore. And that's quite an impact, is it? I mean, well, that's not public knowledge. We don't know, but the news said those jets couldn't down. Sorry?
So, the problem is those planes can only take off if they have their flight plans downloaded onto the plane. And because the database was down, well, they couldn't get the flight plan.
So the comment was that's bad design if configure crashes that system, and I kind of agree. But the thing is, it's probably not because the malware was running on the database and it crashed the database, but it was a side effect, a collateral damage, because configure was trying to brute force all those NetShare accounts, and some people, if you...
They contained the database cluster, and that by that.
Well,
do you have some insights on that?
Actually, no.
All right, then, well. There is another rather interesting example, actually my favorite one. News said that there were 7 devices at the UK Royal Navy infected, and we have a picture of those devices here.
Actually, only of 1.
7 of those. So this counts as a device here, okay? All right. Configure is really one of our favorites. I mean, fortunately, the UK carriers are really rather small. We do have bigger ones in other nations. Anyway, so as every malware, configure is trying to spread to new machines that can be infected, and of course, the core part of that is a scanning routine. You want to port scan or to scan the internet for new victims, all right? And I mean, we've seen malware in the past that did it wrong. Might be a nice addition to this presentation, like Code Red or some others that failed. Of course, what you want to do is you want to scan randomly, okay? So what you need is an algorithm that derives a random IP address from your PRNG, okay? And on Windows, it's the case that this rand function in purple over there only returns a 2-byte value, but an IP address is 4 bytes in size. You know that, okay? So you have to call it twice. One for the first 2 bytes and another time for the second 2 bytes, okay?
Maybe just to add, remember Whaledeck? They used the same session key probably because they forgot to seed the random number generator. The configure guys, they are smarter. They seeded the random number generator.
Yeah, actually that was one problem with Code Red. They forgot to properly seed the random number generator, resulting in all Code Red infected machines scanning the same IP address, a sequence of IP addresses, which basically means only the first one is successful. All right, but the configure guys did it right, and they also noticed that a single call to rand isn't sufficient. They need to call it twice in order to derive 4 random bytes. Let's have a look. Now this is what they did. Next IP address, the lower word, first rand call, for the upper word, the second one. Well, what does it mean, the rand call? Read the documentation. Serve to the MSDN, look up what the rand function does. The rand function returns a pseudo-random integer in the range 0 to rand max. What's the question here? What's rand max? Rand max is defined as the value 0x7FFF. Well, it's pretty random. The problem is that there's one bit missing here. That's always 0. That's not FFFF as it should be. It's 7FFF. All right? So in those two words, the upmost bit is always 0. What does it mean? Anybody?
Australia or never gets scanned.
Right. Maybe not Australia, but you are right. Actually, 2 bits always set to 0, fixed value, so to speak, means only 1 out of 4 possibilities is being produced by this scanner here. And that means, as a result, configure scans only less than 1/4 of the whole IP address space. I mean, they came up with the most successful and sophisticated piece of malware, and they fucked up the random IP address scanner. That's why we included this double fail picture here. Why is it less than 1/4? Because, of course, you have all those bogan IP addresses, the 127/8, stuff like that. And this cannot be scanned anyway, so you even have to subtract that part from the quarter here. Okay? So it's less than 1/4. Okay? You want to tell the geolocation hack?
Yeah. Configure version A wanted to make sure that it doesn't attack any hosts located in the Ukraine. Okay? They didn't send their exploits to Ukrainian machines.
By the way, before you start speculating about the reason, we believe the most meaningful reason is they didn't have a valid shellcode for Ukrainian layout systems, which is understandable.
No, I disagree. I think they are coming, the config authors are coming from the Ukraine, and they don't want to harm their landsmen, right? Yeah, maybe, or yeah, they don't want to get into a fight with the Ukrainians.
Well, that's the media whore.
Now, actually, it was the Russians who just wanted to blame the Ukrainians for writing a desiccated virus.
That's basically about the most, yeah, I think the speculation you can read most often on the news. Either they are Ukrainian or it's the Russians blaming the Ukrainians.
Right, but in the end, it were the Chinese who just wanted to lead a false path.
Pretend to be Russians blaming the Ukrainians.
Yeah. And so on. Okay, so how did configure know that a computer is in the Ukraine?
Well, it's on the
How would
slides.
you do it? Also the keyboard layout of the local machine, yeah. But they also used MaxMind GUIP database, which you can download from a specific link, always updated. And whenever configure starts, it goes to MaxMind and downloads the newest version of the database. Problem was 2 million infected machines when configure A started. MaxMind got DDoSed. So they took down the database. But the logic was still in configure. So we looked at it and thought, if they are not attacking any computers in the internet located in the Ukraine, why don't we move the whole internet to Ukraine? Right? Carrying all those computers was too much. So in the end, what we did, we just had a look at how the MaxMind database is structured, And we wrote our own implementation that just contained the Ukraine. And we said, every query you do, it's always the Ukraine. 6 bytes. Actually, if you pack it, it's 36 bytes. But in the end, the database was 6 bytes. So we went to Maxmire and said, hey, can you please put up this database for us? And they said, nah, we're afraid of DDoS, but we can redirect all the traffic to your page.
Which is good, because we can even log, who is downloading the database and have infection tracking by doing that.
Yeah, so in the end, we ended up with telling all those computers and some peer-to-peer programs, unfortunately, as well, telling that all hosts are in Ukraine.
By the way, the lesson you learned from that is, of course, again, never rely on third-party information. That's the mistake the configure guys did, right? They relied on this GeoIP database they downloaded from some random site. All right, so we could do the infection tracking, and this is what we got. This is like, how do you say, exponentially going down? Okay, so it's quite...
to the front. Exponential decay, yeah.
All right, so we think that's quite an impact. I think that's, oh well, yeah, we have a last one. This is our last thing, and then we are open to answer questions. Yeah, we all know that those botnets are spamming, sending spam emails out, and of course they want to send you mails in your own native language because, I don't know, maybe you don't speak French or something. And there is this one botnet, we don't know which botnet it is, but it's sending out those PayPal fake things. Your PayPal account has been deactivated, stuff like that. Maybe some of you have received those as well. And at some point in time, we received one that looked like this. It's in German. If you can't read German, well, I just have to tell you that it's really, really crappy German. No German person would write like that. And the interesting part is at the very bottom. You have recherché and then some Google Translate link. It's the link that was used to translate the greetings down there. I don't know how it got into their spam template or in the spam email, but it's basically the proof that they use automated means to provide native language spam. All right, so that's the last fail, basically. Thank you for the attention. Yeah, they did. We assume that the original email was in French, and maybe the gang behind it is also in France, from France, or from, I don't know.
Or maybe those were the Ukrainians wanted to blame the French.
Striking back. Questions?
Yeah, I'm interested in how good those evasion techniques currently really are. You've demonstrated some of them, and we've seen such things like 8 years ago in commercial copy protection systems, and it can get much worse than that, what we've seen. The examples you gave, is this the level they are at?
It's not. I mean, I would say, I think I kind of disagree to one of your points. I would say malware is much harder than copy-protected commercial software.
So those were easy examples.
Actually, those were the interesting stuff that we found in malware. There are some standard things that you see in almost any malware. Those are like the exceptions where we think, oh, this is pretty nice. Coming back to commercial software, it's always an arms race. You know, they introduce a new technique and somebody tries to create an anti-technique, and then there's the anti-anti technique, and there's the anti-anti-anti technique, and so on. And for example, if you look at VM Protect, which is protecting the Zeus builder, for example, there's a very nice plugin called IDA Stealth from Jan Nevka, who's studying in Aachen, and he is able to even debug VM protected samples. So it's always an arms race, and you can never say this is really good stuff and it can never be defeated. Everything can be defeated at one stage.
Well, I mean, of course, if you have commercial software, you can also have stuff like USB dongles that take input from the malware, encrypt or decrypt it, send it back. That's really, really hard to circumvent or to break. But we see malware every now and then, every day basically, that uses those virtual machines inside the malware. They implement their own virtual machine and execute code in there. And these are really, really hard to break and to debug or to reverse engineer.
So, okay, just to clarify, I'm more into corporate protection systems, and I've seen this arms race like really 8 years ago. We had this multiple layers of randomized bytecode interpreters in Starforce like 8 years ago. So that's where the arm race really was. And so I'm just asking, how did they catch up? Are they really at that point already, or are the examples that you gave from a very basic level?
Well, then they're at the same level, I would say. It's the same in malware, yes.
There's another question over here.
Yeah, you said you overtook the, I don't know what botnet, but you are in control of the botnet.
Yes.
But there are some people who created and owned this botnet before. Can they do the same thing and simply get their botnet back?
There's one important point about this, and that is you need one node in a relay position that can actually inject data. But during the takeover, we made sure that we control all the relays and that nobody can inject another relay. You know, the -R switch or waiting some time or providing good connectivity, that's how you get into, sorry? No, actually, the original botnet was able to introduce other machines because they were relying on the resources of infected machines. And we don't rely on those resources. We make sure that we control all the resources.
So in the original botnet, the relay architecture was dynamic. Further, other relays could join the botnet. And if you don't provide that, then there's no way to inject the relay. So in theory, yes, they could do the same, but as we are not updating peer lists, or those guys who actually did the stuff, as they are not updating peer lists and allow other relays in, that's not possible to gain control back.
Another question over there.
Why didn't you just tell all relays to distribute the commands to uninstall the malware?
That's
Because it's not compliant with German law.
So you are not allowed to remove the malware, but you're allowed to take it over.
we are not controlling, we are just controlling where the end systems connect to. That's all we control, but we are not sending any software to the end systems because that would be very critical. We would take the autonomy of the owners because we would say, well, they can watch after the machine, so we got to take them over and make sure they are not infected, which is critical from an ethical point of view. Furthermore, it's illegal because German law says, well, you're not allowed to hack into systems. Even if we were allowed to, what about if we take over American machines, CIA machines, FBI machines, NSA machines? In the end, we would have the problem that we can't travel to the US anymore. So there are various reasons why we decided not to push updates or to use our own disinfection tool.
More questions?
Cuba, yeah, but it's not too big.
It's kind of a US state anyway.
Yeah, exactly. Why don't you just tell some guys who don't share the same problem? I mean, I'm not too much into the whole process of. That's just
Repeat the question.
a thought. Only questions? Yeah. Why
Yeah,
don't
don't
you
repeat the question because it's taped.
I'm sorry. Why don't you just tell some guys how to do it who don't share the same problem you got, like politically?
Actually, what we didn't tell you is that we did some research on taking over the Storm botnet, the Weldec botnet, the Configure botnet, and all of these can be taken over. So this is a point we've been discussing very, very intensively in the past. Well, that's a morality question, I would say. Of course, what you can do is you can tell some guy in the Ukraine, you obviously can do these things, please do it for us. Well, it comes down to, do you really want to be responsible for crashing important machines, for instance?
Yeah, but so if you wanted to do something like this, you have to do it as an underground operation. And for actually making sure that your stuff is more reliable than the original malware, you got to do extensive testing in all kinds of systems. And for that, you need partners, right? So you have to have some other people involved. Otherwise, there's a high risk that you break something, and you can break stuff more badly than the original malware authors. And so far, we didn't want to take the risk.
Ah, you're in private beta state. I can dig that.
It's, I mean, let's assume that from a morality standpoint, you say, okay, we can do that. I'm going to take the, I don't know, responsibility. And I don't know, maybe you even have strong partners. You still cannot do this publicly because you cannot afford or cannot risk, I don't know, BBC or some other paper writing about that, because you will have people who are strictly against this, and they have power as well. So you don't want to take this discussion into public.
Actually, if you look at Storm, shortly before we held our talk on 25C3, the botnet was already shrunk to like 1,000 nodes, so actually there was a decrease. With Whaledeck, we were able to talk about this publicly because there was American law enforcement behind it and Microsoft, and nobody wants to mess with either of those. So that's pretty safe, right? There's another question.
I was missing one fail. You guys have previously been talking about this one big exploit in Configure. I'm not sure if you guys are still not able to talk about that, or...
All right, so...
Or if that is... ob das verjährt ist inzwischen.
Okay, so what we didn't tell you in this presentation is that we found an exploit in Configure that allows for, I don't know, re-compromisation of Configure infected machines. So I mean, it's like one of those standard memory compromisation vulnerabilities. You get a shell on the machine and then you basically completely control it. So you could remove Configure or, I don't know, take over the botnet, stuff like that. What was the question again? Why we didn't tell you about that?
If it's still...
Yeah, it's still a hot topic. I mean, if you take a look at Configure infection numbers, they are not going down, but they are still on the rise. So I don't know, I think we have like 7 million infected machines worldwide that show up in the sinkholes nowadays. So that's really, really a huge botnet. So it's kind of a problem to make that information public, because otherwise you guys would go and own 7 million machines, which, I don't know. I mean, it's up to you, but we don't want to be the ones who publish the exploit then. The other thing is that this is not really from the technical details, not really a fail, I would say. It's a very, very tiny mistake they made.
Just a small fail.
More questions? Well, thanks then.